Welcome back, everybody. Hassan asked a hypothetical question. What would happen if during part 4 of the fall 20 test, the second reaction was the one we were supposed to do the labels for instead of the first one? And I just edited it together. So we're going to copy the only product that is formed onto my answer page, explain my choice, give a mechanism for formation of the only product formed, and we're going to describe the role of the reactants. Got our Lewis acids, electron acceptor, Lewis base, synonymous with nucleophile, and we'll take it from there. So here we go. I'll just start with the mechanism. This is a reaction where you do the reaction in water, and in water, a lot of ionic compounds ionize, and mercury acetate is no exception. Electrons going towards the more electronegative O. And we get ACO. And we have to know what AC stands for. I mean, on the test, if you wrote ACO minus, it's fine because it doesn't say you're not allowed to. But I want you to know someday you're going to be just told, draw the ACO. And you better be able to do that. So there's the AC. And here's the O. And it's called acetate. We're going to use it later as a base. Right now, we need an electrophile for our mercury. And I think we might have a question. I'm hearing some possibilities of questions. No, I think we're okay. We have mercury cation. Mercury cations are attractive towards alkene pi electrons. Mercury's got a size that means it can straddle both carbons at the same time. It's so big. So here's our carbons. And the mercury, how many arrows were used to make this intermediate? Just one arrow, 2 electrons. A arrow is 2 electrons. And what's going to happen is you're going to get a partial bond to mercury from one of the carbons that had the pi bond. A partial bond to mercury from, I don't know how that happened, from the other carbon that was in the pi bond. And even a partial pi bond remains. And the plus charge is now in the middle of the triangle. And mercury still has an acetate. That didn't change. And there you go. So you have a partial triangle all the way around. I need to see that. And now we have to get our OH group onto one of the carbons. And it's not from an alcohol in this one, it's from water. So we're not going to get an ether like we did on our little roadmap that we did earlier. We're going to get an alcohol. Backside attack on the more substituted carbon. Those words are going to be written down shortly because we're going to get points for them. Backside attack on the more substituted carbon gives this result here. We've got our carbons. We got our methyl here. We got our new O on top here. Mercury. Yeah, I lost a carbon. And mercury's down here. Where's my colors? Mercury's here. So OH up and mercury down. You didn't need wedges and dashes. Which of the 4 products shows mercury and oxygen on opposite sides and oxygen on the more substituted carbon? It is indeed the second product. So we're going towards this. And how do we get there? This thing has an extra proton. It's the conjugate acid of that. We need the base of acetate. Sorry, the base of acetic acid is acetate. I just used it. And here you're making acetic acid, but more importantly, you're making your desired product here from these guys here. Acetate takes the proton here. And let's do the explaining and then the labeling. So we have only one product there, and we need to explain our choice. Well, the first two products have the right regioselectivity, so let's just talk about regioselectivity here. Yes.
Sorry to cut you off, but so when we need to explain it, right, like our choice, we should talk about like, so starting first, like the location where it is, like the regioselectivity. For the first two, they're similar in the like where each one is, right? But they differ in like the dash and wedge.
Yeah,
And
that's
then
stereoselectivity. Yeah.
yeah, and then so we would talk about the regioselectivity and why it's between those two, and then would you want us to like narrow it down from there?
No, then talk about why this product is better than the first one in terms of stereoselectivity. Yes.
But we wouldn't have to compare it to the last two, since those two.
No, the last two are
wrong.
definitely they're just wrong. Yeah.
Okay.
Regioselectivity took care of them. And you're going to say water attacks the carbon that spends more time with a positive charge, and that's a complete answer right here. Water attacks. It's got a choice between these two carbons, this one and this one. Why does this carbon spend more time with a positive charge? Because it's got three groups on it. 3 carbons attached. Water attacks the carbon. That spends more time. Now, why does that carbon spend more time with a plus charge? And you can just write hyperconjugation right here. I need to see that word. If I don't see that word, you're not getting that point. Oops. There we go. And the stereoselectivity. Why is one a wedge, one a dash? And I need to see the magic words of backside attack. Backside attack puts O on opposite side as mercury. That's about as short as I can make that one. And that's why one's a wedge and one's a dash. Backside attack. Here, this is not backside attack. That'd be a syn attack, and that's not going to happen when you have a triangle intermediate like we do here. And then we're going to hit us up with some labels. We need labels anytime two molecules react with each other. But Hassan's got a question first.
Yeah, okay. For regioselectivity, could we just talk about the fact that the OH would go there because of the 3' carbon, or do we have to word it like how you said, because the carbon spends more time with a plus?
But yeah.
Could we talk about like the fact that it is, since it's a 3'?
Well, you can say a tertiary carbon spends more time with a positive charge as well. You can write that as your answer instead. Tertiary carbon spends more time with a plus than a secondary. But you got to throw the word hyperconjugation in there. That's why it spends more time with a plus charge.
So could we say the more hyperconjugated, like the 3' would be better? Like that's what then that's why the plus charge stays there longer. So we just think that would work. Okay.
That works too. Those words were fine. Everything you said was fine. Yep. And labels. So I don't need labels here because there's only one molecule dissociating, but this is molecule A reacting with molecule B. So which one's the nucleophile? It's this one. It's the attacker. So where the arrow starts is always a nucleophile. Nu. And synonymous with nucleophile. Well, I like to go lubnu, just personal preference. Anytime you say nucleophile, you also say Lewis base. They are synonymous at all times. And ELA is the thing that gets attacked by a nucleophile, always. Electron acceptor. Why would you accept them if you didn't love them? Electrophile. Love electrons. Okay. It's a little out of sequence, but I see this molecule reacting with this one. And here it's reacting with a hydrogen. That's called a proton. So not only are you going to use the Lubnu and ELA, but you better throw your Bronsted in there too. So the attacker is the Lubnu. And the thing that gets attacked is an ELA. And when ELA is getting attacked on a hydrogen, it's a Bronsted acid. It's going to give up that hydrogen to the other molecule. And when the Lubnu is attacking a proton, it's a Bronsted base. There you go. And here's an attacker. And there's the thing getting attacked. Attacker's the Lubnu every time. It's not attacking a hydrogen. Don't you be throwing Bronsted around on this one. This thing's getting attacked. It's an ELA. And I believe every time two molecules met, there was labels for each molecule. Don't think we missed any here. So there we have that. All right. Good session?
Yeah.
That's good. Any last minute questions?
Are you out of time, or is there still like time for like maybe like one more question?
One more question, sure. What you got?
I think okay. So I know we already did retrosynthetic analysis.
Uh-huh.
Could we do maybe one more, like the second one?
The second retro on fall 20 when we come back?
Yeah.
Sounds good. Let's do it.
Professor,
Yes.
in part 1 in fall 2020,
Uh-huh.
I just didn't get how we calculated the K equilibrium.
Let's get that on the screen here. That sounds like a question we can do before we leave this little session here. So part 1, we're not sharing here, are we? Okay. We're talking about going from here down here?
Yes.
All right. So what we have in that reaction is the acid base part goes from here to here. So the acid base step, I can't write there. You better steal it. Coming up. And we'll go back over here. And we need a new page. Okay, so what's happening there is the HOB Sia2 is losing its proton to product 1 and 4-methyl-1 heptine. I believe we did this one the other day. So just quickly here, 1, 2, 3, 4-methyl, 5, 6. And that before when we came down here to get this last step done, we had an O minus and C2 becoming OH. So the reactants are all here for the acid base, and the products are all here, these two. So there's your acid base equilibrium. And this is, it's an alcohol.
Yeah, so the 17 was for the alcohol. I was
Yeah.
looking, I was searching for the alcohol. I said it's definitely not KOH.
Right. Yeah.
Yeah.
The KOH was to get the other part of the mechanism started.
Yeah.
So we're only looking at the part where we're using this acid and then this base. So we're going 10 to 17. And pKq is 10 minus 17.
Yeah, okay, now I get it.
You got it? All
Yes.
right. That's good news. Oh,
Thank you.
-7. And we'll come back and we'll have another small segment when we get back.
Okay.